Now, this video is all about crystal structures of metals. Now, we have four types of crystal structures for metals. The first one is simple cubic as SC, body-centered cubic lattice as BCC, face-centered cubic lattice as FCC, and the last one, hexagonal closed pack HCP. Now we're going to categorize them according to the percentage of occupancy of the atoms, or APF. APF stands for the atomic packing factor. Then we're going to describe each type, dimensions, and we're going to show to you the formulas of the volume of the unit cells and atom. Now let's proceed with the first one, simple cubic. The simple cubic has a single atom that is arranged on this conformation. The center of the atoms are located at the corner or point edges or corners of the unit cell. Now it has 52% of APF or atomic packing factor. And for BCC, it has two atoms. The first atom is located at the center of the structure, and further out of the unit cell, the second atoms the second atom is located at the edges or corners of the unit cell cube. Now it has 68% of APF. For FCC, the atoms are located at the faces and corner edges of the cube unit cell. It has 74% of atomic occupancy or atomic packing factor. And for HCP, if we're going to divide a unit cell into a hexagonal prism, it has 74 atomic packing factor as its percentage. Now, let's describe SC. Atoms are at the corners of the unit cell only, as you can see on the figure. And for BCC, one atom is at the center of the unit cell, and the other atoms are now located at the corners of the unit cell cube. Now for FCC, as you can see on the figure, atoms are at the center of the faces, and the other atoms are located at the corner point edges of the cubic unit cell. And for hexagonal, it has 6 atoms per unit cell. Now, the number of atoms for SC is only 1, for BCC as 2, and for FCC as 4. Now, if we're going to calculate the side edge of an SC in terms of radius, it would be equal to twice of the radius, and the volume of the unit cell itself would be twice of the radius. This is in quantity cube. Okay. Now, remember, if we're going to calculate the volume of a cube, it is equal to side cube. This instance is our side here is in terms of A. Now, if we're going to change it in terms of radius, this becomes 2r cubed. From A cube and substitute the value of A in terms of radius now, this becomes 2r cubed. And for BCC, we have the radius in terms of A as the square root of 3 all over 4. A, the volume would be equal to A cube, or if we're going to substitute this one, okay, in terms of A would be equal to 4r all over the square root of 3. Now, if we're going to substitute it to the volume formula, V now is equal to 4r all over the square root of 3 quantity cube. Now for FCC, the radius now in terms of A is R is equal to the square root of 2 all over 4A. And the volume would be equal to the quantity of 2R, the square root of 2 cube. And for HCP, okay, we're going to bisect the figure. A and B are the sides of the equilateral triangle of the base. And C now is the height of the whole HCP structure. Since a side of the base of hexagonal closed pact is an equilateral triangle, A and B would be equal. So A, B are equal to twice of the radius R. And to solve now for the height C in terms of radius, this is for the square root of 2 all over 3 R. To calculate the volume of HCP, V now would be equal to 3 the square root of 3 all over 2A squared multiplied with height C. Now, if we're going to calculate the volume of an atom or atoms for SC, BCC, FCC, HCP, since SC has a single atom, the volume of the atoms would be equal to 1 multiplied with the volume of the spherical atom as 4 third pi r cubed. And for BCC, remember earlier, BCC has two atoms. So the total volume of the atoms would be 2 multiplied with the volume of spherical atom, 4 third pi r cubed. And FCC volume is calculated as 4 times the volume of the sphere. And for HCP, 6 times the volume of the sphere. And remember that ABF stands for atomic packing factor. And this is calculated as volume taken by atoms all over total volume of the unit cell. Now, if we're going to expand this formula, this becomes atomic packing factor, ABF, would be equal to the number of atoms times the volume of the atoms, okay, all over the volume of the unit cell. Now, density of a unit cell is equal to N as the number of atoms multiplied with M as the molecular weight or atomic mass of an element, metallic element, all over N as the Avogadro's number as 6.022 times 10 raised to 23 atoms per gram or atoms per mole. And we have A here as the side length cube. Okay, this is cube. And let's proceed with the following example as for BCC or body-centered cubic lattice, we have the elements iron, vanadium, niobium, and chromium. And for face-centered cubic lattice, FCC, we have the following metallic elements such as aluminum, nickel, silver, copper, and gold. And for the hexagonal closed packed structure, we have titanium, zinc, magnesium, and cadmium. Now, my next video is all about calculations of metallic crystal structures.